Welcome to this presentation. My name is Amin Goudazi and I'll be presenting to you the expert decision support system for aeroacoustic classification from deconvolved beamforming maps, which I developed with my colleagues Carsten Speer from the German Aerospace Center in Göttingen and Steffen Herbold from the Karlsruhe Institute of Technology. So, first of all, what is an expert support system? What does it achieve and why would I need this? An expert support system supports an expert in his or her work by providing additional information about a problem or task. Our expert support system is able to identify aeroacoustic sources in deconvolved beamforming maps and then obtain their corresponding spectra. It then calculates a variety of aeroacoustic properties based on these spectra and other parameters such as the spatial distribution of the source. Finally, it predicts which sources feature the same source mechanism. This enables aeroacoustic experts to identify and analyze a huge number of sources within minutes. So why would you want to use this? In this image, we see a two-dimensional conventional beamforming result at 3 kHz of a Dornier 728 model. In our paper, we also analyze data from an Airbus A320 model. As we increase the displayed frequency, we see that it is pretty challenging to identify sources here. Since our microphone array is limited by aperture size and discrete microphones, an acoustic source is convoluted with the array's window function. This results in the so-called point spread function, and means that the resolution of our map decreases towards low frequencies and produces artifacts at high frequencies as shown here. Beamforming results in high-dimensional data, which is very difficult to visualize, so normally you would spatially integrate regions in the map that you would want to analyze. This is the ambivalent thing with beamforming. We perform beamforming because we do not know where sources are, but then we integrate regions in the resulting map before we actually know what's in these regions. So how can we identify sources in the beamforming map and then only integrate the regions of these sources? Let's look at the deconvolved cleanest C result. Since cleanest C results in very sparse source representations, we can actually visualize the maps as a point cloud by displaying the frequency on the z-axis. Note how the reconstructed source parts form vertical pillars that are located at the slat tracks, flap side edge, and so on. Note also how the source parts are spatially well localized at high frequencies and scattered around at low frequencies. Based on this observation, we present two approaches on how to detect sources and extract their spectra from this point cloud. The first one is based on the assumption that the source parts are normally distributed at a source location. We call it SINT. The second one locally approximates the distribution and then clusters the point cloud hierarchically using the HDBSCAN algorithm. We call it SIHC. Look at this image of the overall sound pressure level. We can observe source regions, but it's very difficult to see what's going on with the lower part of the slat. The reason for this is that the overall sound pressure level is dominated by a lower frequency noise that is not well localized. When instead ignoring the sound pressure level of the source parts and looking at a logarithmic histogram of how often cleanest C reconstructs the source part at every point, we see that we have a much finer resolution and can identify that there are at least 3 sources on the lower part of the slat. SINT is very straightforward in its application. First, you find the maximum in the histogram. Then you fit a normal distribution to this region and subtract it from the histogram. And then you repeat the process until the maximum within the histogram drops below a threshold. Look at the principal components of the real and fitted distribution, displayed by this red and blue arrow. As you can see, there are some deviations, but the normal distributions fit the source very well. But we're not quite finished yet. We know the source locations and their approximated distributions, but we still want to extract their spectra. Well, because we know the PDF of the sources, we can calculate the probability of each location in the map of belonging to each source. Then we simply assign each point to the source with the highest probability and reject all points that lie below a chosen confidence. Then we integrate all assigned source parts to spectrum. In the image on the right, you can see a threshold of 2 sigma displayed by the red ellipses for the sources. These are the integration areas for the automatically found sources. Here you can see all the source parts from the flap side edge region. The color displays the probability value that they belong to the source. On the right you can see the black line, which is the integrated spectrum from all source parts. That is basically SINT, and it works really well for noisy beamforming maps with high resolution spectra. The second method, how to find sources and obtain their spectra, is based on clustering the source part point cloud. There are many different approaches to clustering. In this case, we need a non-parametric approach that can handle noise. We also need a non-Gaussian approach. While the spatial distribution of the source is mostly Gaussian, the frequency and sound pressure level certainly isn't. But when we cluster data, we actually want to use this information as it allows us to separate spatially overlapping sources. So we choose hierarchical density-based clustering for applications with noise, or in short, HDBSCAN. Since we will use it later again, I want to give a brief overview of what it does. First, we want to know if a point cloud is dense. That means, are there just some random noise points, or are there enough points to form a cluster, which for us is a source? We do this by determining how far you have to look around to find a certain number of neighbor points. From this observation, we can build the so-called condensed cluster tree. On the y-axis, you see the inverse distance between points. On the x-axis, every pixel displays a point in the cluster. So, starting on the top with the maximum distance, all points see all other points. They form one big single cluster. When decreasing the view distance, at some point the cluster will start falling apart and separate into smaller clusters. Eventually, single points will fall out of these subclusters because they are too far away. Now, HDBSCAN can use different distances per cluster, so point clouds can have different densities and shapes. Since we also calculated the reachability of each point, you can also specify how close points must be within their cluster before being rejected as noise. This way we cluster the cleanest C results, based on their scaled coordinates, frequency and sound pressure level. The scaling is necessary because we will calculate the distance in this 4-dimensional space using Euclidean metrics. This is basically SIHC, and again you can see the flap side edge, the assigned source parts and the integrated spectrum. SINT and SIHC both are useful and have different applications. SINT is very robust and you can't really do anything wrong. You choose a threshold after which the iteration stops, so in the worst case you set it too low and then the calculation just takes longer and you have a bunch of really small single location sources which are fitting artifacts. In the second step you set a threshold that drops found sources based on their integrated PDF value. This way you can get rid of these fitting artifacts. SINT works really well with lots of noise, so you can use large Welch FFT block sizes, which results in less averaging and normally in more noise in the source map, but you can also obtain really high resolution spectra. Unfortunately, it can't handle overlapping sources well. SIHC, on the other hand, uses a density parameter, so you have to determine manually how many points there must be in a cluster before it's considered dense. This parameter massively changes the outcome of the clustering result. So you can fine-tune it, but also you have to fine-tune it. The biggest advantage of SIHC is that you also take the frequency and sound pressure level information into account, and you don't assume a Gaussian spatial distribution, so you can handle overlapping sources much better. And the very low frequency source parts are assigned to the correct sources much more frequently than with SINT. Note that with both methods you can simply stack the beamforming results at different Mach numbers, or other variations such as angle of attack. SINT will even profit from this, since the histogram statistics increases. Now that we have a huge number of sources and their spectra at different Mach numbers, we want to cluster these sources again to show which are similar. To do so, we need properties based on which we can do this. Since we often measure different models in different wind tunnels at different Mach numbers, we thought it makes no sense to use absolute properties such as the overall sound pressure level at a specific Mach number. Even worse, if you would do this, a single source observed at different Mach numbers would be probably grouped differently per Mach number, even though the underlying source mechanism has not changed. Instead, we chose to define aeroacoustic properties that are independent of the Mach number, or which can be expressed by their change over Mach number. This means that our method requires measurements at least two different Mach numbers. In our paper, we describe the properties self-similarity, Mach scaling, tonality, source movement, and spatial and spectrum shape. As an example, I will explain to you the property tonality. First of all, for later clustering, the tonality property must be broken down to single-value representations that can be calculated automatically. So let's look at the spectra of a sled track at different Mach numbers. When we run a standard peak detection algorithm over these spectra, The first thing we can do is count how many peaks we found per spectrum and then simply average this number. But when we want to describe how loud the peaks are or at which frequencies they appear, we have a problem. The number of peaks changes from source to source and from Mach number to Mach number, so we can't describe individual peaks. Instead, we try to describe their distribution, which is independent of the number of peaks. Here we can see the distribution of the peak prominence. Note we set a threshold of 3 dB. Below peaks were discarded to prevent the irrelevant peaks dominating the distribution. We found that the gamma distribution approximation normally works really well for the prominence and peak width. For the frequency at which they appear, a log normal distribution works best. These distributions can be broken down to 3 values each: shape, scale, and location parameter. So we just broke down the very complex property tonality to a finite number of numeric features, which we can later use for clustering. In our paper we provide a detailed description of the other properties and their corresponding features and how to calculate them. Together, they form a high-dimensional aeroacoustic feature set. In this space, sources that behave similar should be close together and form a cluster. Let's examine this in 2D. To do so, we take the feature space and project it on 2D using principal component analysis. This way, we orthogonalize our feature space and show the first 2 dimensions containing most information. In these 2 dimensions, only 55% in the information is retained, but what we can see is mostly nothing. To get a better impression of what's going on, we labeled all the sources based on their spectral shape and spatial appearance, so slat track, flap track, etc. Note that our labeling might contain errors, which is why you would want an expert support system in the first place. But look again at the feature map with the colors displaying the source type. We see that the same source types are mostly close together in the map. Note that we did not provide any information of where the sources are located in the map, so that the PCA or clustering later on could cheat somehow. These are only the aeroacoustic properties of the sources at different angles of attack. So how could this be done better than by looking at all the source spectra individually and then cheating in the end by looking at where the source is and calling it a slat track anyway, even though the spectrum looked somewhat different? Well, we use clustering again. Since we do not know the underlying PDF of the clusters in feature space and we do not know how many source types we are looking for, we use HDBSCAN again. But how do we determine the denseness parameter in this case? For determining the sources, we had a visual reference. In this case, we don't. But it turns out there's an easy way to choose it. When increasing the parameter, thus you increase the number of points that a cluster must have at least before it's discarded as noise, the number of resulting clusters decreases. It will actually decrease rapidly in the beginning and at some point stop decreasing or decrease only so slightly. Use this value for a first assessment of the results. In our case, that means the minimum number of points should be 3. We call this clustering method based on aeroacoustic features craft. Let's examine the results of craft. First of all, here we have the numbers of the sources. For every number, we have a variety of angles of attack, and for every single one of them, we have a prediction of which cluster it belongs to, displayed by color, and the number which are equivalent. The -1 means this source does not exist at this angle of attack. We also know the probability of a source belonging to a cluster, which is displayed by the color intensity, so a brighter color means it is more likely that the result is unambiguous. When we examine how the clusters were formed and what they contain, we see that results are very close to our own assessment. For example, cluster 1 is the flapside edge, and cluster 11 includes most of the slat tracks. But more interestingly, look at the 2 slat tracks close to the nacelle. They were clustered with a very high confidence as separate clusters. Looking at their spectra, it becomes obvious why. This is a pretty normal slat track from this airframe. You have the Struhal number scaling peaks here. This is one of the nacelle slat tracks. You don't have the peaks, the noise scales over Helmholtz number, and you have this high frequency hump over here. Consequently, this source was not clustered together with the other slat tracks, which is correct. When we evaluate this result of craft on this dataset, 90% were correct and 4% wrong. The rest was ambiguous. More importantly, none of the wrong classifications were given with a high confidence. They were given because they had a very low probability of belonging to any cluster at all. The Airbus A320 dataset, which we also analyzed in our paper, was clustered with 84% accuracy. To sum this up, we are able to find sources in beamforming maps with SINT and SIG, cluster their aeroacoustic properties, and then group the sources based on these properties with a high accuracy within minutes using Craft. Previously, the sources had to be manually identified and analyzed, which could take months for large datasets with lots of varying parameters. The results provide the aeroacoustic expert a first guideline of how to classify sources and detect anomalous behavior, as we showed with the slats close to the nacelle. Previously, this behavior might have gone completely undetected when integrating over the whole slat, for example. We were also able to detect spurious sources in situ on wind tunnel measurements, since we can use the mean feature values of a cluster to learn about the source. Knowing the location of a source paired with its properties directly after measurement, for example a single tone that scales over Helmholtz number, so it's probably a cavity, we can eliminate the source and redo the measurements. We can also cluster the sources of different datasets together and see which are similar. We can compare source types of different models in their feature space, and finally, quickly evaluate design configurations. This way, we can learn more about the underlying aeroacoustic mechanisms. So, what's left to do and what could be improved about this expert support system? First of all, we showed with a weird behaving slat track that sources often exhibit a different behavior at low and high frequencies. Optimally, we would detect if this is the case before calculating the features and separate the spectrum accordingly into two separate sources. If this is done and we achieve even better results, we could start building labeled datasets from previous measurements and transition towards supervised machine learning. Thank you for your interest in this topic. I hope you enjoyed the presentation and have a look at our paper. If you're also drowning in beamforming data and would like to collaborate on this project, please contact me via email.